Hello everyone and welcome back to our remote sensing lecture series. In the last lecture we discussed radar backscatter and how different surfaces and objects reflect microwave signals in unique ways. Today we are going to build on the foundation and move a step deeper into the mathematics and physics behind these interactions. Our focus will be on the scattering matrix, which is a compact way of representing how a target modifies the polarization state of an incoming radar wave. We will also discuss about coherency and covariance matrix. Before we begin, if you haven't already, please subscribe to the channel, click the bell icon and share this video with your friends or colleagues interested in remote sensing. Let's get started.
Since we have seen the fundamentals of micro remote sensing, we will see how the image data is represented. The area observed by the radar is represented by a matrix S, which is called as scattering matrix. There are four elements of matrix: SHH, SHH, SVH, SVHV and SVV, which gives complete information about the target. In digital image processing, you have learned RGB images. Those are represented using three matrices. First for red, then second for green and third for blue. Each pixel in RGB image has three values. In PolSAR image, each pixel has four values from four polarization combination. Once we get the scattering matrix, we can use mathematical knowledge to derive coherency and covariance matrix. Okay, it's a second order statistic. The coherency matrix generally represented by T. Okay, so this is the coherency matrix T, which is closely related to the physical and geometric properties of the scattering process and thus allows better and direct physical interpretation. So now here you can see, okay, T is formed from a vector called known as Pauli scattering vector. Okay, and how that Pauli vector is calculated with the help of the parameters of scattering matrix. Okay, so once we get this T has how many elements? There are total 9 elements. Okay, T11, T33. So there are 9 elements which we got from the coherency matrix T3. Now here, okay, T11, all diagonal elements, T11, T22 and T33 are real values, okay, real elements, and rest are imaginary, real imaginary, okay. So this T11, T22 and T33 components gives information about single bounce, double bounce and volume scattering, which are generally represented by blue, red and green color respectively. So you can calculate the value. You will get the T11, you will get T22, T33, okay, from HH and HV and VV, okay. And what they have done for just for representation purpose, this is what it is, a single bounce. Now what is single bounce? The backscatter which is received from the surface of the water, okay. So they have given the color blue, okay, and this is a double bounce. What is double bounce? A man-made target. So generally it is represented by pink or red color. And the last is volume. So volume is represented by a green color. Okay.
Now we will walk through how to go from the raw PolSAR scattering matrix to the covariance matrix and what that matrix actually tells us about the target. Start with the scattering matrix S. For a monostatic SAR pixel, we write S equals a 2 by 2 matrix with elements SHH, SHV in the top row and SVH, SVV in the bottom row. Remember that Sij are complex numbers. They carry amplitude and phase and they represent how the target scatters energy from a transmitted polarization I to a received polarization J. Next, let's clarify an important practical distinction: reciprocity. With reciprocity, which holds for most natural targets, and in most monostatic SAR systems, we have SHV equals SVH. In words, cross-polar return is symmetric. Under this assumption, there are only three independent complex channels, SHH, SHV and SVV. In that case, we form the lexicographic scattering vector with three components as shown here. This three-component vector KL is what most spaceborne PolSAR pipelines use because most satellite sensors and natural scenes satisfy reciprocity. Without reciprocity, which you might see in bistatic radars or uncommon anisotropic scatterers, SHV is not equal to SVH. Then all four channels are independent and the lexicographic scattering vector becomes as shown here. Non-reciprocal data are rare in civilian datasets, but you should be aware of them when working with experimental or bistatic systems. Now, how do we get the covariance matrix C from this scattering vector? We compute the outer product of the lexicographic vector with its Hermitian transpose and then average. That average is commonly a spatial or multilook average to reduce speckle noise. In compact form, C equals the expectation or multilook average or KL times KL Hermitian transpose. Here the brackets denote multilooking, averaging over a small window of neighboring pixels, and a superscript H means conjugate transpose. If we assume reciprocity and use the three-component vector, the covariance matrix is a 3x3 Hermitian matrix whose entries are averaged pairwise products of the S elements. Explicitly as shown here, the matrix C, which represents a covariance matrix. The diagonal elements are powers or intensities. For example, SHH star is the averaged HH power. The off-diagonals are complex cross terms. They carry relative phase and coherence information between channels. Because C is Hermitian, the lower triangle is the complex conjugate of the upper triangle. If reciprocity does not hold, you build the same type of matrix from the 4-component vector and obtained a 4x4 covariance matrix. Same principle, more channels. Before we finish, a quick interpretation about what we discuss. In the Pauli or coherency representation, the three principal components often map intuitively to scattering mechanisms: single bounce, that is surface, double bounce, that is dihedral or man-made, and volume scattering, that is vegetation, and are often shown as blue, red and green respectively in Pauli RGB composites. In the lexicographic covariance formulation, the diagonal term give you channel powers and off diagonals tell you about relative phase or coherence. Both are essential inputs for classification and decomposition algorithms. It's useful to know how the covariance matrix is related to the coherency matrix T, which you might already have seen. The coherency matrix is formed in the Pauli basis rather than the lexicographic basis. T and C contain the same second-order statistical information. They are just expressed in different bases. A unitary transform U converts one to the other. So choosing C versus T is often a matter of convenience or which basis makes subsequent interpretation or algorithm simple.